This is our discussion for chapter 3. Today we're going to talk about center and spread. We're going to really get into what we mean by a distribution and how distributions can look. There's a lot of ways that data can present themselves, how people can respond overall to different variables, and so it's going to be good to understand what we mean by distribution and the general types that we see in practice. So this is a good quote from Sherlock Holmes, very applicable. You can read it whenever you want. So when we talk about distributions, one way to kind of visualize them is with a histogram. When we look at a histogram, there's a lot of different ways that the data can come out. So one of them is bell-shaped, and that's this nice, what we're going to call normal curve. It's symmetrical, it's unimodal, it has a lot of nice features that we'll end up using throughout the class. But you're also going to see a lot of other types of distributions. You're going to see things like bimodal, so you have two peaks in this data. You have right skewed, and if you remember, right skewed, the tail is pointing to the right. So when we say right skewed, it's pointing to the right. So left skewed would have the tail the opposite direction. You have this J-shaped, which is basically when you have a floor or ceiling effect happening where a lot of people are right at the bottom or right at the top. You also see ceiling effects with U-shaped. U-shaped is rare in the wild, but I have come across it a few times where people are either really low on the score or really high, and very few are in the middle. And then the last one we have on here is uniform, which just means you have roughly the same number of people in basically across the whole variable itself. So a normal distribution or bell shape means that most people are right in the middle towards the mean. Uniform means they're just as likely to be anywhere. When we're talking about center, we want to talk about where the center of a distribution is. We have three ways of doing that. We have the mean, median, and mode. The mean is the average, the arithmetic average. So you add them all up and divide by how many there are. What happens when you use this is it's going to tell you a very specific balance point of your data. It is notably not resistant, which means it's influenced by extreme values or outliers. So if you have an outlier, the mean is going to chase it. It's going to go in that direction. There's alternative forms of the mean, like a trimmed mean. We don't use that a whole lot in practice. You may come across it a few times. In general, in the population, the mean is symbolized by this character. It's called a mu. And it's just equal to the sum of the scores divided by everyone in the population. In general, we're actually going to be using a sample, and it's going to be denoted as this X bar. So that's a bar on top of it. APA uses an M often, but again, it's just the sum of all the scores divided by however many there are in the sample. When it comes to the median, it is the 50th percentile. It's actually the middle value. So the mean is the balance point. The median is the middle value. So if you order all the values from lowest to highest, it is the middle value. If you have an odd number of values, then it's just the middle value. If you have an even number of values, then it's the average of the two that are in the middle, because there's not just one in the middle. The median, you always can remember it because half of the values are above and half are below. What's nice is that it's easy for a computer to do. It's not always fun to put all the values in order and finding the middle. But if you have to do it on an exam, it'll only be a handful of numbers, and we'll usually put it in the order for you. what's nice about the median is it's not influenced by just a few extreme values or outliers. You have to have a lot of extreme values in order for it to start to get pulled in that direction. The last one, and maybe the easiest, is just whatever has the most, the largest frequency, the highest peak. One issue with modes is that it's not necessarily unique. You can have more than one mode. If there's more than one value that has the same number of people that responded that value, then you can have more than one. And it is probably the furthest from what I would call center. Your mode can be on the far left or far right of your distribution. And you end up using this a lot more with categorical data than you do with mean and median. And in fact, you often don't even do a whole lot of the mode anyway. So I said that the mean is a balance point. So if you look at these distributions here, the mean is going to be the point that balances the distribution. So of these three, you can look at them and see what point is balancing it. And of course, in this case, it's this one. So this would be the mean point. Now, if we're looking at the median, it's probably more like this point right here. So the median isn't going to balance it. It's just going to be the middle value. And when you have a right skew, the median is going to be slightly to the left, if not a lot to the left, of the mean. So the mean is a balance point. The median is the actual 50th percentile. Half of the values are above, half are below. When you have a symmetrical distribution, so like a bell-curved one, for example, the mean and the median will be approximately the same. So when you have a nice symmetry in your distribution, both of those are going to be around the same point. One way to really think about this concretely is looking at the distribution of the annual household income in the United States. You may not be super surprised by this. There's a lot of inequality in the US, and so you have a lot of people. The mode is actually at 15 to less than 20,000. And you have the vast majority of people are over here, earning less than 40,000. The median household income was roughly 50 grand. So half of the people in the US earned less than 50 grand, and half of the people in the US earned more than that. What's interesting, the mean household income was roughly $75,000. So if we're trying to entice someone to come to the United States, we might say, well, the mean household income was $75,000. But the issue with the mean here in this distribution is that these ultra wealthy individuals, so if you're into sports like Steph Curry, who's making a ton of money, or Jeff Bezos, which is just, he makes billions of dollars every couple of days essentially when Amazon's doing good, it's pulling the mean up really high because it's trying to balance out those really high values. So this will be balanced. What that means is that there's a massive gap between the median income and the mean income. In situations where it's highly skewed, generally the median is going to tell us what the center is a little bit better than the mean. The mean is still going to tell us something. It's going to tell us a balance point. But the median is going to tell us where half of people are below and half are above. So again, the median is resistant and doesn't change much. The mean is influenced and changes quite a bit more. So consider this very simple example where we have all of these people over here, and this is the mean in that situation. And if we just add one person over here, just one, it scoots the mean. And in this case, it doesn't scoot it a ton, but it does scoot it. just one individual can have that effect on the mean. Where with a median, you can add that one person and it stays the exact same. The median is right here the whole time. So it's really important to remember that average does not mean typical. If we had someone really far outlying, let's see, if we had someone really far out here, really further out, then the mean might be a value that no one actually scored. So we could have a mean of 4 if this value was far enough out. So the average does not mean typical. So that's our discussion about talking about the center of a distribution. Where is the center of it? But that's only part of the story. When we talk about distribution, we also need to talk about the spread of that distribution. Because two distributions could have the exact same mean and median, but one could be far more spread out than the other. To talk about that, we're going to use things like range, IQR, and SIR. SIR we're not going to rely on a whole lot. These are really good to really just understand really basic information about the spread of your data. We're going to be relying a lot on variance and standard deviation throughout this class, and so we'll talk about what those are and what the calculations mean in just a moment. With range, it's just the max minus the min. So you just find the highest value and you minus the lowest value, and that's your range. You also have this, what's called the interquartile range. And that's where you find your 75th percentile or your Q3 point. And you find your 25th percentile or Q1 point, and you take the difference between those, and that's your IQR, or interquartile range. You also have this other version, the SIR. We're not going to use that a whole lot in the class, but just so you're aware of what the calculation is, it's Q3 minus Q1 divided by 2. So one more thing about range and IQR is it's not as impacted by the type of distribution you have. You just have max or min or the Q3 and Q1. So you're just finding percentiles essentially. When it comes to the variance, you're going to be using the mean. And so anything that affects the mean is also going to affect the variance. So outliers that do affect the mean are also going to affect the variance. So what is the variance even talking about? Well, it's the deviance. So how far from the mean is an individual? When we calculate the full variance, it's going to tell us the average deviance essentially. When we get to the standard deviation, that's actually the interpretation of it. The variance is the step prior to that, and it's going to be something we use throughout this class. So we use the square, so the pluses and minus don't cancel out to 0, because if we just minus the mean and add those all up, the mean is the balance point, and so what we end up having is the sum will always be 0 when you take all the values minus the mean and you just sum that up. So we do the square. The square makes it so they're all positive values. So what we end up having is what's called the sum of squares. Sum of squares is literally just the sum of the squared deviations from the mean. So you're taking your value minus the mean, squaring it, then you add the next value minus the mean squared plus the next value. And that gives you your sum of squares. Using that divided by our degrees of freedom, which we'll define more carefully later on, in this case it's just n minus 1. If we divide by n minus 1 here, that's going to give us what is called our MS, our mean squared value. And our MS is also signified with this sigma squared value. Ultimately, these are the same thing. So MS and the squared value, you're going to see both in this class, so they're talking about the same thing. In the population, this is the equation. In a sample, that's normally denoted as s squared, it's going to look like this. So you're going to use n minus 1 for these. And for all of our stuff, we're going to be using a sample, and so n minus 1 is how it's going to be for the variance. So all this is trying to do is trying to take the average deviation from the mean in the sample. So it's saying, on average, how far away are people from the mean? If the variance is bigger, that means on average people are further away from the mean than if the variance is smaller. From the variance, because it's in these squared terms, you actually can take the square root of it, and that's going to give you what's called the standard deviation. And that is actually in the units of our original value, and so that's going to tell us the deviation a lot more clearly, because it's going to be in the units that we actually want to talk about. So the variance is going to be in these squared units. The standard deviation is in the units of whatever variable we're getting the standard deviation of. And the standard deviation is going to be that average deviation in the units of your variable. So one thing to keep in mind is the perfect estimator does not exist. In other words, there's not a summary statistic that is the best, that just works all the time. So some rules of thumb are you can use a median and SIR or IQR with skewed data, or if you have really big outliers. And the mean and SD are going to generally be with a symmetrical and there's no outliers. But honestly, in practice, I report the median, the mean, and the SD, and often the IQR every time, no matter what the distribution is. Together, they paint a pretty full picture of what the distribution looks like in your data. But as you might have guessed, with my bias, a graph usually gives the best overall picture of a distribution. So these summary statistics are going to give us a lot of good information, but a graph can usually tell the full story much, much quicker. So when it comes to the mean and SD, since they're both relying on the mean ultimately, it's good to understand some properties of them. So if you do something to the values in your data, you can understand what is going to happen to the mean and the standard deviation. So for example, if you add or subtract the same constant number onto every score, the mean is going to add or subtract the same amount. So whatever you added to everything, the mean is just going to move up by that much or move down by that much. And then the standard deviation doesn't change. So let's say we have some data on how many words someone got right in a test of intelligibility. So they're trying to understand someone with a lot of background noise, and we're trying to understand how many they were getting right. And then we find out, oh, we miscalculated it. Everyone should have scored 3 words higher. So if we add 3 to everyone's score, the mean is going to move up 3 points, and the standard deviation will go unchanged. If we're multiplying or dividing the same constant number onto every score, the mean is going to multiply or divide by the same amount, and so will the standard deviation. So for example, if we were calculating everyone's height in inches and we change it to centimeters, that calculation, the change from inches to centimeters, that multiplication, the mean will multiply by that same amount, and so will the standard deviation in that new calculation, so in the centimeters version. So the mean and standard deviation move very predictably when we make any changes to the data. But remember, if we make the change, in this case, these properties we're talking about to everybody, not just to some individuals in the data. With that background, we need to talk about 2 new words, skewness and kurtosis. Skew is the degree of symmetry in the distribution. Generally, you can detect this visually with a histogram or a boxplot. Skewness statistic, which I'll show here, is a calculation with a cubic term. What it's trying to do is find the skewness. General rule of thumb is any skewness that's plus 2 or minus 2, so -2 or a +2, that's generally taken as a sign of skewed data. So if that value is positive, then it's a right skew or a positive skew. If the value on the skewness is negative, then it's a left skew or a negative skew. And then if it's 0 or close to 0, then that means there's no skew. In other words, it's symmetric. So you can see here that the tail is pointing to the left, so you have a left skew here. No skew, there's no tail pointing in either direction. And then a right skew, and the tail's pointing in that direction. Kurtosis, on the other hand, is a really lengthy calculation. It's not something you have to memorize. You don't need to memorize skew or kurtosis. What you need to remember is what it means. Now, kurtosis is the degree of flatness in a distribution. This one is a bit harder to detect visually, but still possible in some cases. The kurtosis statistic itself is based on deviations from the mean raised to the 4th power. It's the math of magic, if you catch my drift. Again, greater than or less than the +2 or less than -2. So if it's more extreme than a +2 or a -2, it's a sign of problems with kurtosis. When it comes to interpreting kurtosis, a positive value means it's leptokurtic. It means it's really peaked. I'm going to show a picture in just a moment about it. A negative value is platykurtic, means it's really flat. Or 0 means it's mesokurtic, which is normal. It's kind of a nice bell curve. So here's some examples. Kurtosis of 0 is a nice normal distribution. Kurtosis that's positive, it's peaked. Kurtosis that's negative, it's really flat. So with those terms, understanding the center and spread, with just the terms that we've talked about today, we can really describe what the distribution is for any given variable. We can start to talk about if it's a normal distribution with a symmetric shape and the kurtosis is close to 0, or if it's really peaked or really flat or skewed. Those things are all really important to very carefully understand before you move on to any other analyses like a t-test or ANOVA. So now we're going to talk about the 5-number summary. And it's going to be intimately tied to boxplots. So we're going to just do an example with very small amount of data. And the 5-number summary is really important because it tells you a lot about the distribution of the data in a fairly succinct way. So to start, the median is going to be the middle value. So you find the min and the max. So we have the min at 77, the max at 99. And we find the middle value. There's an even number of values here, so the median is the average of these, which gives us 86.5. And we can mark those points, so the min, median, and max on this number line. And then we can find the Q1 and Q3 value. So Q1 is you take the lower part, so below the median, and you find the median values of those values. So in this case, if we're just looking at these, we find these middle values. So Q1 is 79.5, and the upper values for Q3 are these middle numbers, so we get 90.5. We can mark those too, so we mark here and here. And then if we connect the lines, we get what's called a box plot. So a box plot has the min, the first quartile, the median, the third quartile, and the max. We call it the 5-number summary: min, Q1, Q2, Q3, and the max. A box plot is also going to tell you a bit about the distribution. So if this is really long over here, then you might have a skew going on. The IQR here is going to be the 90.5, which is our Q3, minus the 79.5, which is our Q1, and that gives us 11. And then you also have this semi-interquartile range, which will be the 5.5, because it's just the IQR divided by 2. And just to make it clear, the box plot and the histogram will tell you very similar things. So when you have this nice normal distribution, the box plot's going to look pretty symmetrical on all sides, and the median's going to be pretty close to the middle of the box. When you have, oh, and another thing, when it's a normal distribution, the distances here are similar. They're not massively different, like in this case where you have a really plateaued histogram. The box part's going to get really fat and the whisker part's going to be small. When it's skewed, it's going to look like this, where one side's really small from the median and the other side's really long. And then most box plots now, if this distance, the max, is too far away, it's usually defined by a measure of the interquartile range. It'll mark those points that are too far away as dots. They usually hint at extreme values. In R, this will automatically be done for you. It'll show you those points that are just a little too far away. So this is actually a box plot in R. So you can see these extreme values here. You can tell that this is the placebo and the treatment group. And the box plot here is telling us there is some overlap between these, but the treatment group is higher. They have a higher test score than the placebo group. But again, some people in the placebo group did just as well as a lot of people in the treatment. So a box plot tells you a lot of information really quickly. You also can look at density plots to understand these. These are like smooth histograms. So you can do this just across all the groups, or you can do it by group to understand how they might differ. So in this case, this pink group is higher in a lot of cases than the green group, although there's a lot of overlap. Another way to understand the distribution of our data is using what's called a QQ plot. And this uses theoretical locations and the actual locations of your data to try to see if it is normally distributed. And if the dots run along the line, then your distribution is roughly normal. So in this case, it is roughly normal. The dots, for the most part, fall along the line. There's a little bit of a deviation, so it's not a perfectly normal distribution, but it's pretty normal here. Often you'll see this shape be like a crescent shape in some way, or an S shape, and that usually tells you that it's not normally distributed. So let's apply this. We're going to again apply it to the cancer data set. And as we've done before, we're going to use Rio to import it. We're going to use a Tidyverse Rio furniture and psych package. For the import, you can also use a couple other functions to import SPSS data files, but import is probably your best bet. Next step is we can clean it. So we brought it in, we named it Cancer Raw, and then we're grabbing Cancer Raw and then renaming all to lower, and then creating a variable called ID. Turns out ID is already in the data, so we're just changing this one to a factor. And then we're changing treatment to a factor with the labels being placebo and aloe juice. And then we're making stage a factor as well. So in essence, we're just told R, the ID should be categorical, treatment should be categorical with these labels, and stage should be categorical. From there, we can get the frequency table. Age is a continuous variable here, so it doesn't show us all the labels. It's showing us 8 of them, or 9 in this case. Must be a typo. So this is just showing there's a person that's 27, all the way up to 86. We can do that for the treatment. We can see that 14 were placebo and 11 were aloe juice in this data set. We also can use the package psych and the function describe to get, sorry about that, to get the N, so the complete number of responses, the mean, the SD, the median, the trimmed mean. I don't use the MAD really ever. The min, max, range, gets the skew, the kurtosis, and then we'll talk about what SE means later on. But it gives you all of that information for all the variables that you want to. In this case, we're just saying grab this data and then select these columns and then describe them for me. So here, age, we have 25 complete cases. The mean is 59.6. The SD is 12.9. The median is 60. So the mean and median are very close to each other, which would suggest the distribution is symmetrical. We also can look at the skew to see that. And it says it is. It's not bigger than +2 or lower than -2. And kurtosis is really small too. So age is really normally distributed. And we could do that for all of these other variables as well. So glancing at this data, you can see total C weigh-in. So this is, I think, cholesterol at intake. It is approaching problematic skew, and it has a problematic kurtosis. So it's this positive one, which if we go back, positive kurtosis means that it's really highly peaked. So we have a kurtosis of 4, which means this one looks a little bit skewed and peaked because of the values we're seeing for it. The others don't seem to have a problematic value for kurtosis or skew. And just as a note, when I say problematic, it just means it's something we need to look into more. We need to understand why it's skewed. We need to understand why there's kurtosis. But we don't, it doesn't mean that we can't run analyses on it. We're going to find out there's a lot of ways we can still work with this data. We also can get other summary statistics, so counts in percentages or means and standard deviations using table 1. It's all happening here. This is just for everybody. This one is grouping by treatment. And we also can get a box plot. And we're going to show a number of these. Because this is a recording, I'm going to go fairly quickly through this, and you can always come back and look at each of these. But there's a lot of ways you can look through the data set. So here, in AES, we're saying, so we're creating a blank canvas with ggplot. Turns out we can just put AES inside of the ggplot function, or you can have it after. Either way works. The AES here, we just tell it X is just this full sample, and that's just a label. That's just a label that we're giving it, and it'll show it here. And then Y is age. It's not in quotes, that means it's a variable. And so we're just looking at the distribution of age. And then we just say plus geom boxplot. So age is on the Y-axis. X is just a label of full sample. And so we can see there's an individual that's kind of far away from everyone else. But overall, this is a pretty normal distribution from a box plot standpoint. We can group it using the fill argument in AES, so we can fill by treatment. What that's going to do is create a box plot for each of the levels of whatever you told it to fill by. So we can see the age differences across these two. So what it looks like is the aloe juice has a larger distribution, a wider distribution than the placebo group in terms of age. So the variance in SD and range and IQR would be bigger for this group than this one. We also can do this by just telling it that we want our X value to be the treatment group, and it will just make it so the X value is the treatment. We also can facet by this, so we can use facet grid. So we can say we want this by treatment, and then it's going to create a facet for each one. We also can decide, I want to do this for a subset of individuals. So to grab a subset, we can say we want to grab our data and then filter. We want to just grab those that weigh in. So weigh at intake is less than 172. We want to know what their ages are. And then we can, again, use the ggplot and geom boxplot like we've been using. And we can find out the distribution of ages for those that at baseline were less than 172 pounds. We can do it by multiple conditions if we want as well. We can say we want to filter by weigh-in is greater than or equal to 150 and treatment is equal to placebo. So what this means is this distribution of age is for those that weighed at least 150 pounds and are in the placebo group. To show another one where we can use in, we can say we want those in the aloe juice group, and the stage needs to be in 2, 3, or 4. So we want just the second, third, and fourth times they came in. So that's what that line is doing. And then again, this is just creating that box plot. Now, when we want to look at multiple variables in the same figure, one of the things that is really helpful is using this gather function. And what you tell it, this is just the name of the variable you want to have the time variable in, and this is just where the values will go. And then you tell it all the variables you want to use. So when you have repeated measures, this is one way we're going to do this. For example, when we have repeated measures ANOVA later on, we're going to use an approach like this. All it's doing is reformatting the data for us so that we can use it in a better way. We'll be able to talk about this more in class. I can show an example. There's actually a lot of ways in R to do this. The gather way is a little bit outdated, but it still works for our purposes. So we'll probably end up using that in this class. Here, all of these are the same measurement, but at different times. This is at intake, week 2, week 4, and week 6. So all we're doing is taking those and combining them so that we have a time variable and a value variable. So time is now the name of the variables. So intake, week 2, week 4, week 6. And the value is just going to be whatever value they had for these. So at intake, their value for cholesterol was here. Week 2 is here, or cancer. I can't remember what that variable stands for. Don't quote me on that. But the idea is it looks like it's going up until about week 6, and then it levels off. So this part If you have questions, please ask in class. It is a more advanced data feature, but it's something that you can definitely figure out and understand. It'll just be helpful to see some examples. So in class, we can show a few of those. And of course, we can make a box plot as complicated as we want. I mentioned ggplot can do just about anything we want it to. So we can do repeated measures by group and by stage. So we have all sorts of information that we can go on. And I'm just remembering now, stage is the category of cancer. It's stage 4, stage 2 cancer, not the time point. So there's multiple time points and stages and their values, and we can put that all into a single figure to highlight what is happening across groups and stages. So in this case, it looks like for the placebo group, they're also going up. But it looks like stage 4 goes up pretty sharply, while stage 2 kind of levels off. Whereas here, stage 2 has a similar pattern where it goes up and then levels off. But stage 4 doesn't keep going up. It goes up and then down. So pretty quickly we can understand general patterns in our data before running any statistics by using a Boxplot and using faceting and colors. So please post any questions you had about this on the discussion board. We'll be able to talk about this in class, address any remaining questions about the analyses themselves, about moving the data, the gather function. But most importantly is understanding what these concepts mean, what center and spread mean, and how we can understand those. Our next topic will be standardization and normality. It's going to heavily build off of what we talked about today, so you want to understand these concepts because we're going to be building on those to understand what standardization and normality are.